the next project, we are once again going into a different sector. So we had energy production in the first talk. We have now sustainable buildings and panels. And now we move to a complete new sector, textiles. For this, I welcome Anna Cissé, who will tell us a lot about the Cellfil project. She sits currently at Quantis, Switzerland, and I'm really curious to hear your talk, how to make textile applications more sustainable.
Thank you for the introduction. Hi, everyone. So I'm pleased to present to you the Cellfil project today with a focus on environmental LCA for bio-based filaments, notably lyocell filament in the context of this project. Unfortunately, I won't have any first results to share today, so I'll be focusing more on the place of LCA within this project and the role it has to play. But first of all, let me give you a quick introduction to the project itself. So Cellfil is working across several levels of the textile value chain. This makes it very specific, very special in a sense. So it aims to optimize lyocell filament feedstocks and yarn production, which includes shifts within the feedstock from a 100% primary raw material, the wood pulp-based lyocell filament, to a material which integrates either second-gen materials or part of alternative feedstocks such as orange pulp. It also looks at yarn functionalization, textile processing routes such as weaving and knitting, and how the filament in the end can be used for different end-use applications. It will also address market uptake and scale-up potentials in further steps. And what's really important here is that it's not only about changing a yarn, it's that we're going beyond this and looking at the full value chain of the product. And this is where LCA becomes interesting because it helps to connect material choices with the processes of implementation and innovation within this value chain. Before I dive into the LCA topic with more detail, I wanted to provide some further high-level context. So what is very challenging for the textile sector as a whole is closing material cycles. As of now, less than 1% of materials in clothing is recycled back into textile fibers. And another issue from the textile value chain can also be related to microplastics. For instance, in Europe, 8% of microplastics which land and oceans come from synthetic textiles. Of course, I will not make this a debate about synthetic versus natural fibers. Where this project is interesting is that it assesses how bio-based filaments can be made even more circular by the integration of, for instance, byproducts of other industries or by using recycled materials as such. Of course, there's also a dimension which is more on the side of social aspects and economic aspects as well, but these I will not be speaking about just now today. So with this, I would like to tell you a bit more about the end-use applications that we're looking at in Cellfil. So this is one very interesting aspect of the project because we're going to look at very different potential end uses. One of them being performance apparel, and then others being automotive textiles and composites and technical rubber reinforcements. So here, of course, we have a project where different LCAs will be done for different contexts. And this also will provide a variety of insights as one filament might work well for performance apparel, why it may not for automotive textiles, for example. So where do we stand within the Cellfil project regarding LCA at the moment? So Cellfil still has another 2 years to run, which means that we have not final preliminary results at this stage. Of course, we have computed some first results for just the filament level, but there's still some refinements going on, and our current work is focusing on the next processing steps, more the weaving and the knitting, and the additional inventory information to get to the end-use applications. What's also interesting about this project is really that it covers the full life cycle. So we're looking at the cradle-to-grave impacts, and we'll be comparing at different levels within this project the impacts of the filament for starters, but also of the end-use applications, of course. So what does this mean concretely? I was mentioning before, so LCA here serves as a tool for different levels of application. We'll look at cradle-to-gate impacts for the filament, for example, to understand how the recycled content will shift the results and how the orange pulp may affect the results at filament level. And later then we're going to be assessing the specific end-use products for the different industries included in the project. We are mainly working with the primary data from the partners, and where necessary, we'll add some secondary data. One thing that's interesting as a basis for solid assumptions making in this specific sector is to rely in parts on the PEFCR apparel and footwear, so the product environmental footprint category rules, which were published last year, where Quantis was the technical lead. So this will allow us to make sure that we have solid aligned assumptions where necessary, because we do not have the primary information, which is also specifically relevant when we go beyond the factory gate. One additional point here is that, of course, we will have different functional units depending on what we're looking at, which can be per kilogram at the filament level, but which will go beyond this when we're looking at the function of the final products. If the functional units will be different if you're looking at, for example, a sports shoe, for example, or be it the cover for a car seat, for example. I mentioned it before, so we're looking at the cradle-to-grave and environmental impacts for these different systems. What we will focus on is to make sure that we look in more detail at the life cycle stages which are most relevant, given the changes that will be made from the baseline to the respective new products in the comparisons. And with this, I wanted to take some time to get a bit more concrete about what we're going to look at within this project. So LCA is relevant at different levels. At the feedstock level, this will help to provide insights about the 100% lyocell filament versus its mix with orange fibers, or versus the mix with second-gen fibers. Then we'll also have a look at the processing and how this new feedstocks may affect the processing in the end. And very important, of course, we'll look at those end-use applications to understand where where conventional feedstocks can be replaced and to what extent, and to understand how this will change and affect the environmental performance of these end products. One very interesting part of this project is as well that we will be looking at end of life with quite some interest. So looking at what are the potential benefits of bio-based fibers, and how can this be relevant for the circularity of the different products. You've heard it also in previous presentations. In the end, for LCA, what's very important is to use the right methods to assess and provide the right insights and complete insights for the different materials of interest. So within this project, we're using ES 3.1 as a lifecycle impact assessment method. And beyond a cutoff approach, which we will do in the first stage, we will also be looking at the results applying the circular footprint formula. This is specifically relevant for the context of having a recycled content or some sort of recycling at the end of life, as this allows to allocate burdens and credits between the supplier and the user of the recycled materials. And especially for the end-use applications where some synthetic materials might be replaced by bio-based fibers, we will also look at plastic leakage to see how this replacement may affect this element. And with this, I'm already through my presentation, so I'm giving back a bit of time to the ones coming next. I'm well aware this was quite technical, but I think one key aspect is to keep in mind how LCA can be a powerful tool to support innovation throughout the process.